Hi everyone, this is Dr. Fryer. It's March 3rd, 2025, and I would like to go over how to answer questions 3 and 4 on the study guide, which involve linear and binary searches. This is actually my second attempt at this, and hopefully I'll be a little bit more efficient this time. So when you're thinking about linear versus binary search, binary is going to be more efficient, and you're going to want to use it. However, binary search has got to have a sorted list, and in the case of the example we're going to be doing, it is alphabetized, and because it is alphabetized, we're going to be able to do this divide by 2, and make these comparisons. So linear search checks everything one by one. Binary search is going to be dividing the list in half repeatedly. And so linear is going to be slow for large lists. It's still doable, but the binary is the one that we're really going to like because it's going to be faster with large lists, okay? So those are kind of the key takeaways here. So let's look at problem 3. Now, problem 3 asks us to use the binary search algorithm, but I want to go ahead and do a linear search to show you how this works. Now, this particular list happens to be sorted, right? It's alphabetized from, A to W or whatever. It's from the descending order. It wouldn't have to be a sorted list for us to do a linear search. But to do a linear search, we're going to start item by item. And in this case, if we were going to search for the word cow, if I can get back to my pen here. Okay, we're going to start out with index 0. So for index 0, it's the word 8, and that is not cow, so that's not going to be it. We're going to go to index 1, and that happens to be cow. And yeah, that's it. We get it. I mean, it just happens that it's right there as number 2. But theoretically, cow could be all the way at the end, and so it could take us a lot longer to do that with a linear search. Linear search is each one at a time. Compare whatever you're looking for to each item in your list. Okay, let's go down to binary search now. The binary search algorithm is going to have us calculate L, M, and H, where L is going to be the low and H is going to be the high. I can that right? And then M is, pardon me, it's going to be the middle. And M is going to be calculated by adding the low and the high and dividing by 2. All right, so let's do the first one. We're looking for the word cow. So for the search for cow, the low is going to be 0. The high is going to be 10, right? Because we're doing this entire list right now. And M is going to be 5. We'll round down if we need to. And again, we get that by adding those up and dividing by 2. So 0 plus 10 divided by 2 equals 5. So M in this case is 5. Now, we are going to be comparing our search term. In this case, it's cow, to whatever the index term is for M. So in this case, it's 5. So we are looking at cow compared to owl, and we're looking at how they fall in the alphabet. Okay, cow comes before owl, C comes before O. So we can mark out the right side of the list. Remember, this is a sorted list. And we know that our search term, if it's in the list, is going to be in this left-hand side. Okay, so I'm now ready. I'll switch colors and let's be green. I'm now ready for my next iteration. My next iteration is still going to have a low of 0. But instead of having a high of 5, I'm going to subtract 1, minus 1, okay, to get my H. And so I'm going to be working with 4 because I already compared it to 5. I know it's not 5, and I know it's to the left, so I'm going to start with 4, okay? Now I need to figure out my M, what's in between. Again, 0 plus 4 divided by 2. 4 divided by 2 is 2. I am going to be comparing now to the 2. And so I look at eel, and I compare owl with eel. And I know, I said owl. I'm going to compare cow with eel. And cow comes earlier in the alphabet than eel. So again, I know that I can mark out these, and I'm only working with these 2 now. All right? My low is still 0. My high is now 1. And my M is actually going to be 1. It would be a half, but I'm gonna round to 1. So I'm going to be comparing it to 1. Oh, and look at what I find. They're the same, cow, cow. So that means I have found my result. And so the index is going to be a 1. A positive 1 is going to be returned when we find the search term that we're looking for. Okay? All right, now let's go ahead and do one more, and this is going to be looking for the word sow. We're going to use the same list that we had before. Okay, oops, let me get my eraser, sorry. Why does that keep on going back? I just want to erase. All right, so I'm going to erase my annotations here, and it's going to leave my terms. Haha. Okay, and so now we're going to look for the word sow. Okay, you can just look at the list and see that sow is not in there. Okay, so the index that's going to be returned is going to be a -1. When the binary search algorithm does not find the term, it does not return a +1, as we did in this first one, it returns a -1. But I need to show you the algorithm and how this works. So again, it's going to start the same. L is going to be 0, the H is going to be 10, and the M is going to be 5. We're going to start by comparing our search term, sow, to what we find with 5. And in this case, owl and sow obviously are not the same, so that's not it. But sow, the S of sow, comes after the O of owl in the alphabet. So this time we mark out everything to the left, and we know that we are now working between 6 and 10. We know it's not 5, okay? So it's between 6 and 10. So the next iteration of our search is going to be 6 as our low. It's going to be 10 as our high. And again, we can calculate, it's going to be 8 in the middle. You can say 6 plus 10 divided by 2 is 16 divided by 2. It's 8. And so now, excuse me, we are comparing our search term sow to 8, okay? Now, 8 is not T, and so it's not a match. And in this case, we know that the S is going to be to the left of T. T is later in the alphabet than S, so we can actually mark out all of these. We know it's not 8, it's not to the right, it only leaves us these two, okay? So for this search, our low is still 6, but our high is 7, and our M, I guess our M is actually 6, we round down. And so we go ahead and compare, and in this case, we find that the comparison of sow to the S of sow to the P of pick means that it's going to be to the right, but I don't have any more that I can find to the right. Is that right? I think that is. Maybe it still leaves me with 7, and I end up doing one more, because I'm actually comparing it to 6. I know it's not this, and it just leaves 7. So I think for the last one, we end up comparing it, so we just have 7. 7 is our high and our low, and then it compares, and we don't find it, okay? It's not rat. When you do not find the result, it returns a -1, and I actually think it has to do with one number being less than or greater than the other one, but that's the best I can do at this point to show you the entire sequence of search when you are not finding the result, and it's going to return an index of -1. Okay, I hope that is helpful. Let's go on down to problem 4. Problem 4 has a couple different parts, and it includes asking us to tell what is going to go in this JavaScript formula that describes the linear search algorithm, okay? Linear search algorithm. So remember, the linear search algorithm, we did it over here, is comparing every single one. Compare cow to 8, oh, there it is. You compare each one in turn, all right? So here is what is going to go in the blanks. This is these are the answers, okay? We need to know what's going to go in, and I guess I can use my highlighter here. Is this my highlighter? These 5 spots, okay? That's the question. This is the answer, okay? These things are going to go in those boxes. And what it's asking is, the list length is how long your index is. In this case, it was 10 for what we were doing. The list item is going to be I, and it's going to be looking for the target. And we were first looking for cow, and then we were looking for sow. Those were the targets. And again, this is the return. If it returns the index, okay, it returns I, and it says it's a match. And if it doesn't, it returns a -1, okay? Actually, I think that means that here for cow, okay, it's not always a +1. The reason why this is, sorry to make this correction, the reason why this returns a 1 is because that's what the index is, okay? The index for cow is 1, and that's why it returns a 1. It always returns a -1 if it doesn't find it, okay? All right, there you go. So both of our questions here are helping us clarify. So here's what you need to write into this problem, okay, when it's asking you for the JavaScript. This is going to be the list.length, okay? It's going to be searching for the list item, and then the target, that's the actual, in this case, word that we were looking for, like sow or cow. And it's going to return that number, okay? That actually is what helped me just get that one right over here and say that it's a 1. It's returning the number of the index, okay? If it finds it in the list, if it finds it. But if it doesn't find it, it returns a -1, okay? So those are the 5 things that you're going to need to fill into that JavaScript for it to correctly have correct syntax, all right? Okay, the very last thing, and I actually didn't go over this in the last video, that was the last attempt. Given the following time efficiencies for algorithms, exponential, logarithmic, linear, or polynomial, rank them in order from most efficient to least efficient, okay? The most efficient is going to be logarithmic, okay? And that is what we're doing as a binary search, okay? It gets faster every time because we cut it in half every time. That is going to be most efficient. The next most efficient is actually linear. Even though we said linear is going to be slower with larger lists, it's more efficient than these other options, and it's second, okay? The third most efficient list, and it's the third in the list, okay, next to worst, is polynomial, okay? And one of the examples of a polynomial search is a bubble sort. I don't actually think that's on the test, but I'll confirm that. And it is growing as you're doing the search, and it's getting slower and slower, okay? The least efficient, the worst search is the exponential search. And the reason for this, and I guess an example of this is recursive Fibonacci search. It becomes unreasonable. It becomes so big to calculate because it grows so fast, okay? So logarithmic is getting smaller, it's faster, it's the most efficient. Exponential is the worst. Those are the order that you're going to want to put them in: logarithmic, linear, polynomial, exponential. And the reason that exponential, it says which of the efficiencies is unreasonable, it's exponential. And the reason is because it becomes impossible to calculate, okay? Because the search terms and the size of the calculations calculate. It becomes impossible to calculate because it just grows so quickly. It becomes unwieldy and just ginormous, okay? All right, I hope that is helpful to you. I apologize that I had to do this again. Hopefully I got it a little bit faster. I don't know if I did or not, but we'll talk about this more in class.